I gotta do that to make it be the thing. All right, cool. You know how I forget what comedian was it? I can't remember now. Um, I can't remember now. But you know how you're using a plastic to pay, right? Like a credit or a debit card, and you slide the thing into the machine, and a lot of them have chips anymore, so you got to leave it inserted. But like the one I'm really thinking about is at the gas station, right? So or if you've got a swipe card that doesn't have a chip, right? I still have a couple of those. If you swipe it wrong, like if you swipe it too slow or you swipe it too fast, it yells at you, it beeps and tells you to do it again. Why? What's the problem? Why, when you insert the card into the gas station, terminal there, do you have to remove it quickly as opposed to like slowly pulling it out, or insert it and then really quick take it out? Or like, why is there a right way to do that? And what does that have to do with these sort of objectives, things that we're supposed to talk about in this particular topic? I will give you a minute to look those over. I'm not going to read them to you. Although I will say, that's an interesting word. A circulating electric field? That's not normal. We're not used to that. The four fundamental, wait a minute. The four fundamental equations that completely describe electricity and magnetism, the whole stupid thing? Wait a minute, this is going to be a cool topic. All right, I'm excited now. There it is. Hey, it's almost like I knew this slide was coming. Why must you remove the card quickly instead of just leaving it there? Energy conversion. Well, that's an interesting thought. That there's some sort of relationship between the energy that mechanical energy we're using to apply a force to the card to pull it, that there's some work done, and that gets converted into some kind of like electromagnetic kind of something. That's a thought. Faraday's law is the big news in this particular topic, because we're going to keep coming back to Faraday's law. There's a couple extra things at the end, but most of the meat and potatoes here is Faraday's law. Maxwell's equations, not actually Maxwell's equations. They actually are more due to Oliver Heaviside than James Clerk Maxwell. But we're really excited about Maxwell because I'll get to it. What is induction in this context? What is electromagnetic induction? during the 1830s. Now, if we can put this together with our discussion from Tuesday, recall that it was only in 1820 that Ørsted published his findings about the interplay between a current in a wire and a magnetic field. So it only took 10 years for us to really start digging into this phenomenon. A coil of wire is connected to a galvanometer. Remember, a galvanometer detects current, essentially. If we hold a magnet nearby and don't do anything with it, nothing happens. The galvanometer detects no current. But if we move the magnet towards the coil or away from it, while it is moving, the galvanometer shows some current flowing in the coil. There's no battery, there is no source of EMF in this circuit. It's just a coil of wire and a meter. That's it. But apparently, something about moving the magnet caused there to be current in the wire. Which I suppose makes a certain amount of sense. It's like the backwards of Ampere's law. Essentially, Ampere's law talks about how field is created by current, and now we're kind of the other way, how currents are created by fields. But it's not. This is interesting. In order for there to be a current, there needs to be an EMF. There's got to be a voltage. There's got to be an electric field. A current creates a magnetic field, and a moving magnet creates, apparently, an electric field. That's interesting. A moving charge creates a magnetic field. That's what we talked about on Tuesday. And here we're saying a moving magnet apparently creates an electric field. Suppose we replace the permanent magnet with a different coil connected to an EMF, connected to a battery. Turn the current on, and just as we said a couple, I think it was maybe before spring break, the loop of current, in this case it's a coil, but it's multiple loops of current, behave like magnetic dipoles. It behaves like a permanent magnet. I expect it to do the same thing that the permanent magnet did. If we move the powered coil towards or away from the other sort of passive coil, we detect current. If we just hold the powered coil steady, we don't measure any current. Suppose we keep them both stationary and use a switch to turn the current on or off. Great. Again, we detect current, but only when something changes. Only right when the switch is toggled from one setting to the other, we get a pulse of current, and then we're back to zero. If we turn it the other way, then we get a pulse the other way, and we're back to zero. So it appears to be the case that a changing magnetic field of any in any sense, moving the coil means that we're exposing the passive one to a different magnitude field, right? As we get closer to the pole of a magnet, the field lines get closer together and the field strength increases. So if we put that closer to the coil, it's a stronger field. So we've changed something about the magnetic field as experienced by the passive coil. If we turn on the switch and leave it sort of stuck in, like in this particular slide, we are changing the presence of the magnetic field sort of wholesale, all at once. Okay. What if we change the strength of the field? What if we change the shape of the coil? Ooh, that's an interesting one. And apparently, any of these factors, magnetic field is constant, and the shape, location, and orientation of the coil do not change, then we measure no current. But if we change any of those things, the field, the shape, location, or orientation of the coil, we measure a current while that thing is changing. Once it's done changing, we measure no more current. It doesn't matter what the state is, it only matters how it changes. And there's one more fact that is salient for our analysis here. The faster we do any of these changes, the more rapid the change in any of these quantities, the greater the current we measure. Double the field strength using this north-south sort of magnet engine here. Electromagnet, probably. Double the magnetic field in 10 seconds. We measure some amount of current the whole time. Double the amount of magnetic field in half the time, we measure twice the current while it's changing during those 5 seconds. All right. In order to quantify this, we've got to look at units. We've got to make sure the units work out. We want to say something about the fact that the magnetic situation is changing and say something about volts, right? Because we end up with EMF from someplace in the passive coil. If a current flows through a coil with non-zero resistance, there must have been some EMF to do that. How much? Okay, so we got to think about the units and make sure the units work out. We've got to think about a thing, some sort of quantity, some sort of measurable thing that depends on shape, location, and orientation of a coil and field strength. That's the second thing. Third thing, we've got to account for how much time it takes. back before break, when we first started talking about magnetic field, we said that we could write a Gauss's law for magnetic field, but it wouldn't do any good because the answer is always zero. We wrote that. Which we didn't really do anything with. We were just sort of like, oh yeah, okay. The fact that it's zero means that there are no magnetic single poled objects. It's got to be north and south. It's got to be a magnetic dipole. Otherwise, it's not real. No such animal. And we said that, and we kind of walked away from it. But this is a thing, right? I mean, this is kind of by the same definition we used back when we were talking about Gauss's law for electric fields. We said the net electric flux through a closed surface was E dot dA. And that had something to do with the charge enclosed. Now, the equal sign, it's not super, the equal sign is not super important. It was Q over epsilon, but that's neither here nor there. The point was, this integral represents the net flux, the net electric flux, this one. But we could, stop that. We could also talk about the magnetic flux. Now, the net magnetic flux through a closed surface, a surface that bounds a volume, is going to be zero. Because there are no magnetic monopoles. But if I'm looking for a thing that talks about the shape and orientation of the coil, now the dot product that is represented there, that handles the orientation. The area in question, we're talking about the shape and size. The location has to do maybe, I don't know, in a uniform field, the location doesn't matter. But if this field were non-uniform, if this were a loop nearby a magnet, moving the loop up and down or moving the magnet up and down, even though the magnetic field is constant, our interaction with it, our exposure to it changes, right? So that's, I guess, the location piece. But in the picture here, a uniform magnetic field, that's not, we're talking about field strength, but the field strength, that's B here. So I'm looking at magnetic flux, the magnetic flux through this surface, the surface bounded by the loop. It's not a surface that bounds a volume. It is a surface that is itself bound by a path. And that's the same stuff we were talking about on Tuesday when we were talking about Ampere's law. We were talking about the circulation of the magnetic field around a closed path that bounds a surface. So it makes sense, I guess, that we're talking about a non-closed surface that is itself bounded by a closed path, because that's what we were talking about on Tuesday. But here, we're not interested in the circulation. We're interested in the flux. Just want to remind you how magnetic flux would work, because we didn't really talk about it all that much before break, because we said, well, the net flux is 0, so we don't need to worry about it. Suppose we have some small area dA. The area vector is defined this way, up. The magnetic field points this way. The angle between those two things is this measured angle phi. And if we want to know the flux through this little differential area, we need B perpendicular to the surface, which uses cosine of the angle, full magnitude dA cosine of the angle, but this is B dot dA if we define as a vector. Okay, cool. If the loop, if the surface in question is oriented such that its area vector is parallel to the magnetic field, then the flux is just the product. Field strength B times area A. That was a lot of words. It looks like the surface and the field are perpendicular, and they are. But the area vector is also perpendicular to the surface, which means the area vector is parallel to the field. We had similar considerations to worry about back when we were talking about Gauss's law for electric fields. If we change the angle, we change the flux through the surface. If the magnetic field is directed within the plane of the surface, in other words, if the area vector is perpendicular to the field, then the flux is 0, because the dot product does that. All right, so this is a thing that talks about, in one fell swoop, the field strength as perceived as a result either of a changing magnitude field or of a proximity to a non-uniform field. And it talks about the orientation of the thing with respect to the field, and it talks about the size of the thing as experiencing the field. That's pretty much all the stuff we wanted to say, except for the rate issue. The faster we do this, the bigger the response. So we want something. So if it's proportional to the rate, then it's inversely proportional to how much time it takes. I'm starting to feel like I'm talking about a derivative. Faraday's law. The rate of change of magnetic flux that handles all the pieces should be should be at least proportional to the induced EMF. Okay. At a minimum, I think that is proportional to what are the units of this thing? Now, the slide here says something about the unit of magnetic flux is the Weber, and 1 Tesla meter squared is 1 Weber. So 1 volt is 1 Weber per second, which doesn't really follow for me. I mean, it makes it sound like if the one thing is true, then the other thing must be true, kind of by looking. And I'm looking at it going, I don't, what? Why? So I want to unpack that a little bit. Flux per time, right? This thing has the units of flux per time. Flux has the unit of field times area over seconds, let's say. Dimensionality of time, but seconds. Now, area, it would be meters squared. Now, okay, so we know we know Tesla, but what is a Tesla? Like, how do we? Oh shoot! All right, if it's me, I always got to go all the way back to like fundamental, like 231 style metric units, and then work my way forward. I'm thinking about F equals QVB. We talked about that before break. It's supposed to be a vector arrow there. There we go. So newtons, coulombs, meters per second, Tesla. So a Tesla is a Newton second per Coulomb meter. All right, cool. Now we're in business. Damn it. Newton second per Coulomb meter times meter squared. Okay, so that's, wait a minute, I lost the seconds. So the seconds cancel, we lose a meter, and we've got Newton meters per Coulomb. Newton meters is joules. Joules per Coulomb. So this is energy divided by charge. But energy divided by charge, yeah, that does in fact have the unit of volts. So I'm perfectly happy replacing that with an equal sign. Check mark. This does exactly the job we wanted it to do. The only funky thing here is The minus sign. What's the deal with the minus sign? That's a good question. I'll answer that question. But I'm going to wait a minute before I do it. Let's look at a couple examples. Suppose we have a circular conductor. It's not a disk. It's a circle. We're highlighting the area such that we have area vector A, and we can use the right-hand rule, I suppose. We choose the direction of the area so that we walk around the wire loop in the right-handed direction and the thumb points up. So let's say the area vector points up. Suppose the magnetic field also points generally up, in this case, up and to the left, an angle phi. And what we're going to do is increase the field strength somehow, perhaps by moving the wire coil closer to a permanent magnet, increasing the field strength. Maybe. Or we're just using a stronger dipole or something. Increasing the flux, so the time derivative is positive and the EMF is negative. Now, what does that mean? Well, we use the right-hand rule. Current would flow in the direction of our fingers, but the EMF is negative. Okay, so it flows the other way as drawn. So it all comes back to the right hand, which again makes sense because that's where we started when we were talking about magnets. It's all about, well, when we were talking about magnetic fields anyway, it's all about the right hand. What if we decrease the field instead? Okay, so as far as we're concerned, the time derivative of the flux is negative, which means the EMF should be positive. And now the current flows in the direction of our right-handed, walking around the loop. A couple more examples. That's the upside down. We're still defining the area vector as pointing up, which means our right hand is still in the same orientation. The positive direction around this loop is counterclockwise as I'm looking at it. The dot product of the field and the area is negative. If we increase the field strength, it becomes a negative number of larger magnitude. So it becomes more negative, in other words. d phi dt is negative, which means the EMF is positive and the EMF flows in the positive direction, counterclockwise, as shown. And to round out the set, what if we have a field in this direction that we decrease? The current flows the other way. One quick note, our drawings originally were of coils, not of loops. How does that change things? Well, a coil basically just has a bunch of loops. I mean, it's basically, especially if you pack it pretty tightly, it's basically just a stack of loops that are all connected in series. So whatever happened to one loop should happen to all of them. And we can just multiply by the number of windings or the number of turns or the number of loops in the coil, whatever you want to call them. I still am curious about this minus sign. Like, I suppose it's clear enough which way the EMF points. Like, it all comes back to the right-hand rule. But it feels, well, no pun intended, but it feels a little bit hand wavy. Maybe there's another way we can think about this. If there were a current flowing in a wire, the current's flowing clockwise, or I'm sorry, counterclockwise, as we're looking at it. And therefore, the EMF also points that way. That current, now we showed this on Tuesday, that current would manifest a magnetic field. In which direction? According to the right-hand rule. Okay. Hang on a second. Let me go back a few slides. When we decrease the field strength of a positive flux, we induce an EMF that points the other way. Points the other way. What other way? What is he talking about? That points, we had so and so much flux. We had an original magnetic field vector, and we had an original area. And then we took that and reduced it. The field that would be created by the induced EMF points in the direction to try to put back the flux that we're losing. It's almost like a flux conservation kind of way. Like, the direction of the current is so that the current tries to oppose the change that's happening in the flux. We're taking flux away, so it's going to try to put some back. Here, we're adding some flux. So it's going to try to take some away. Current's going to flow the other way, and according to the right-hand rule, the field that is created by that current is oriented opposite the field that we are increasing. So it's trying to sort of zero out the change in flux. It's trying to adjust for that. Same story here. Adding more negative flux means that the current is going to try to put positive flux to balance out. Taking away negative flux means that the current is going to try to put back negative flux. The field that would be created by a current going clockwise points down. in the direction of the field whose strength is decreasing. We're trying to put back the flux. We're trying to oppose the change. We call this Lenz's law, but it's basically just a restatement of the minus sign that lives in Faraday's law. What is the like significance of that minus sign? This one? Well, Lenz's law is a way to state what its significance is. Makes it easier than trying to figure out, wait, is it this? Did I have my hand the right way? Did I define my area vector the right way? It doesn't matter. Whatever the change is, the current that is induced will try to oppose that change. A couple examples. Moving the magnet, looking at the left figure, moving the magnet closer to the loop increases the field strength, which points down through the loop. So the induced field wants to oppose that, which means the current needs to be counterclockwise. Yep, and there it is. If we move the magnet the other way, the reverse happens. Oh, wait a minute. if we move the magnet the other way and turn it around, we had positive flux up through the loop, and we are taking it away by making the field weaker, which means it's going to try to put it back. I looked at these diagrams a second too long, and I started to get really confused what this thing is. What is that pointing to? Where is that curve coming from? And it's not anything. It's just an indication that these two things, the direction of the current and the induced field that we're showing, are both associated with Lenz's law. That's all. It's just we're pointing to the consequences of Lenz's law. It's not that there's another weird curving vector here that we got to worry about. We're just pointing out what's going on. Turn things around, use the reverse situation, we get the reverse effect. While we're here, let's actually look at a problem together.
In conceptual example 29.8, we're going to use Lenz's law to find the direction of the induced current for the coil sitting in a magnetic field as shown in this diagram.
Oh.
The magnetic field points straight up and it's increasing in magnitude.
This is the same thing we just talked about. It's the same picture we looked at, isn't it? That's just this. Well, that's not very much fun. Do we have a problem for flux that we can look at? Yes, we do. Aha. Let's check this one out.
In example 29.1, we're going to examine the EMF and current induced in a loop that's in a regional space where the magnetic field is changing. Specifically, between the two poles of a magnet, the magnetic field is increasing at a rate of 0.02 Tesla per second. The loop, shown in yellow, has a total area of 120 square centimeters and a total resistance of 5 ohms. In part A of the problem, we're going to find the induced EMF in this loop and the current that's flowing through the loop. In part B, we're going to replace the loop by an insulator and ask what happens to the EMF and the induced current.
The area, its magnitude is increasing. Find the induced EMF and the induced current. So we're going to use Faraday's law. We know the area of the loop. We know its orientation with respect to the field. And we know, ooh, interesting. We don't know the actual field strength. So at no point can we calculate the actual magnetic flux through this loop. All we know is the rate of change of the magnetic field. Hopefully that's not an issue. There's only one loop, so we don't need to worry about capital N for like a solenoid or anything, a coil. I think we can start by writing things down. Let's write Faraday's law.
So the two equations we'll need for this problem are equation 29.2, which gives us the flux through the loop, which of course in this case is simply going to be the magnetic field times the area. And the second equation is Faraday's law of induction, which states that the voltage going around the loop is equal to minus the change in flux through the loop. So we're ready to begin. So since the magnetic field and the area vector are parallel to each other, again the flux is simply B times A, but B is changing with time. So d phi dt is really...
Wait a minute. That came really fast. Hold on. D phi dt is the derivative of the product field times area. Because nothing about the orientation is changing. So whatever the field strength B is, the dot product is B dot A, which is just B times the magnitude of A. Okay, but if we're taking the derivative of the product, A, the area of the loop, is constant. So we can pull that outside the derivative. And all we are left with is the rate of change of the field itself, dB dt, which is exactly what's given to us. And our video tutor just plugs that right in. Induced EMF, there we go.
Really just A times dB dt is shown here. And I have dBt from the narrative of the problem. And I have the area, and so I get a voltage of 0.24 millivolts in magnitude. The magnitude of the current that's flowing is this voltage divided by the resistance.
It's just Ohm's law. The only resistance in the circuit is the resistance of the loop itself. And we've got an EMF and we know the resistance and we can find the current. Yeah. So I guess the moral of this story, if we're talking if we're talking about induced EMF, that means we're not done talking about EMF, is I guess what that means, which means we're not done talking about Ohm's law. We're not done necessarily talking about loop rules and junction, like I don't know, but as soon as we bring EMF back into the conversation, we're talking about all of our like DC circuits work from before break, which is okay. You know, in the physics class, right, you do expect to have to bring some stuff with you as you go. It's just worth noting, I think.
That's 0.048 milliamps. So if I replace the conducting loop with an insulator, the induced EMF does not change because it doesn't depend upon the resistance of the loop. However, the resistance of the loop now is infinity because it's an insulator, and so the corresponding current is going to be 0. And finally, I note if I take the loop completely,
I guess we're meant to assume that it's a perfect insulator. A much better question, in my opinion, what if we replaced this loop with a material of, I don't know, greater resistivity? What would happen to the current? Would it increase, decrease, stay the same? And we would say, well, it decreases because there's more resistance, but the EMF is the same because the EMF is a result of the field parameters and doesn't care what the composition of the loop itself is.
out from between the poles of the magnet, there's still an EMF that's associated with a circular electric field between these poles. And this ends example 29.1.
What was that last bit? A minute, say that again.
An example 29 loop. However, the resistance of the loop now is infinity because it's an insulator, and so the corresponding current is going to be 0. And finally, I note if I take the loop completely out from between the poles of the magnet, there's still an EMF.
Take the loop, the wire loop, move it completely away from the situation, throw it out.
That's associated with a circular electric field between these poles.
There is still an induced EMF. Even if there's no charges to move, even if there's no pipe for the current to flow in, there's still an induced EMF. Nothing about Faraday's law says anything about the fact that there needs to be present a wire in order for the EMF to cause current. All we know is that there's an EMF. And if there's an EMF, it's because there is an electric field. And that's what our guy just said.
And current's going to be 0. And finally, I note if I take the loop completely out from between the poles of the magnet, there's still an EMF that's associated with a circular electric field between these poles.
A circular electric field. Whoa. That's pretty wild. Okay. Current flowed. Because we're just talking about an Amperian loop, right? And the flux going through a surface. It doesn't matter whether there's actually wire there or not. So there's an EMF that points in a circle regardless. It's sort of like, well, it's lucky that the wire was there so that the EMF could do a thing. But even if it weren't there, the EMF would still be trying to create a circular loop of current. There would still be an electric field that's trying to do that, even if there's no, medium for current to flow in. There's still an electric field that is induced. That's wild. A changing magnetic field in free space creates an electric field in free space. Just there it goes. There it is. It is not at all the same as the electric field that comes from like Coulomb's law. It's not pincushion or, well, I guess pincushion or porcupine for negative or positive charges. It's not radially symmetric at all. It's circular. That's pretty crazy. The interesting thing about that, electrostatic force, the force due to a permanent arrangement of charge, whether it's a point charge or a handful of point charges or a continuous charge distribution, the electric field created by that distribution of charge exerts forces that are conservative. If we go in a closed path around a positive charge, that, or near a positive charge, that path, the electric field created by that positive charge does zero net work altogether. It pushes us away as we walk away, and then as we come back the other way against the field, we're doing the field is doing negative work exactly in cancellation for the positive work that it did on the way out. This field, this induced field, doesn't do that. This induced field points in a loop. If we start and go around and come back to where we end, we just did exactly what the field wants us to do the entire time. There's no chance to stop, turn around, and come back so that the field does negative work. We go in a closed path, the field is doing positive work the whole time. This is a non-conservative electric field. Now that I think about it, so is a battery. Battery pushes us It does some amount of work. The battery does non-zero work. We have to do, work is done going through a resistor or so. But the battery, so like EMF generally, whether it's a battery or induced, is able to do work. I mean, that's the whole point. We can do work on the charges to move them so that we can transfer the energy to something else. EMF, that's why we classify EMF as something different, a different kind of potential difference. It doesn't make any sense to talk about an electric potential associated with an induced field like this because it's not conservative. There is no potential energy per unit charge, at least not that we can define. So because there's no potential energy per unit charge that we can define, which means there's no electric potential. And I think a battery EMF has the same problem. We can't talk about the electric potential in a circuit. We can talk about the electric potential difference. You know what I mean? Like, we got a battery, we got a loop of wire, and that's it. It's going to push charge around and come back. The whole time, that is the direction that the battery wanted it to go. That's not conservative. I mean, I guess if we walked up the battery and then turned around and came back, that would be a conservative path. But a conservative force should be path independent. If we start at the negative terminal, are pulled through the battery and sent around, that's a closed path in which the battery did non-zero work on us. And I guess that's why we sort of separate EMF from other potential differences, because it is a different kind of animal. I think it's clear enough that this thing, this induced circular field, is electric field, is cannot be conservative and has to be something other than a Coulombic electric field. This is not the electric field produced by a static distribution of charge. This is the electric field induced by a changing magnetic field, a fundamentally different kind of field. Still an electric field, and still perfectly capable of causing current to flow in a circuit.